Well, let the video begin. I welcome you to lissajou's figures second part, which is also the second video because it's the second part, so obvious, isn't it? And in this figure, and in this video we will be talking about, we will be talking about symmetries, which is most generally, always, I guess, twofold. Twofold. Sorry for that. Which is most generally twofold or fourfold. Twofold or onefold. By fold, I mean planes of symmetry, and since they are like 2D figures, I think saying lines of symmetry will suffice. And sometimes in this video I will be using LF, which will denote to lissajou's figure. And also you can see that okay, sorry, I wanted to do this. Also you can see that some figures, oh my god, also you can see that some figures have, what I am talking about, sorry, I am erasing that. You can see that some figures have twofold of symmetry. It's like two lines of symmetry. Some figures have a single line of symmetry, and some figures are don't have line of symmetry, but they have what I like to call a center of symmetry. And these two are, I'm sorry, I will change the color. These two are rigidly related, because in explaining I will be dividing it to 4 quarters, and this can also be explained by dividing it into 4 quarters. I will try to find some connection between this part and this part, which I will also try to do in this case. But this case is slightly different because it has only one line, so the thing that I have to do here twice, I need to do here only once. So that's the special case. It is this is a problem that I did not know how to start, where to start. But once I got in my mind that I can start dividing it into 4 quarters, and that basically solved it. You can also try this, but I will present my views on it. So let's start. By the way, for the first segment of the video, which will deal about figures like this and figures like this, I will be doing it physically on the piece of paper and with the help of pen and markers. And I have already done it, but I can say you the results that the pen and paper did not turn out to be that good. Rather, the digital one turned out to be better, because in the digital one you actually have a plain sheet. Any orientation that you write in, it is a plain paper always. But on the on the physical one, it is a bit difficult, because I need to position my camera somewhere, but it doesn't I can't place it in a particular angle. Well, let me start by drawing the figure. Let's just fast forward this. This is just me drawing, which is not necessary for you to see. Actually, not at all necessary for to see even this clip also. since this is like a general video, so I won't be assuming my convention which I explained in the previous video. Rather, I will be just sticking to the general convention, which is to consider this orientation of rotation as the positive rotation, and the the phase to start from this line. So this is like the 0 phase line, and let me open this real quick. Difference, yeah. So the phase difference is pi by 2, and the angular frequency ratio is 1 by 3. So I mean, I will be assuming that this as 1 omega naught and this as 2 omega naught, and yeah, so let's start. So pi by 2 is the phase difference, so I will assume this line to be the initial line for this rotation, which is like pi by 2 ahead of 0 phase, and it rotates in the usual convention positive direction, and this to start from here, which is the G0 phase, so that now the phase difference is pi by 2. I mean, in essence, one should not talk about phase difference in like different frequency, I mean while comparing, but like since it is like a butterfly effect, like initially if you have different conditions, it can lead to the different figures. So yeah, as is evident from these figures. So let us first divide the figure into 4 segments. Like if it would have been a 3D figure, I would have considered dividing it into 8 octants, but since it's a 2D figure, I will divide it into 4 quarters. And of these 1 quarters, I will only have my focus on this particular segment. I will darken that up with this pen. Which is evident that on this circle it will determine this quarter, the same quarter line, I mean. And on this circle it will be somewhat like at this point. We will try to find what this angle exactly is, but for now let's assume that it is theta. Since we know, I mean, sorry, it's like 3 omega, as you can see right here. I hope you can see that. So when it rotates 90 degree to perform this segment, and since it's like 3 omega naught, this pointer needs to move by 90 degree by 3 degree, so it's like 30 degree. So now we found out then that when this moves 1 quarter, it moves only 30 degrees. So this is what this angle is, since this segment is formed by the culmination of the rotation through this circle and this circle, and since the ratio is 1:3, the rotation angles need to be in the same ratio. So it's like 90 degrees to 30 degree. Yeah. So now what we have found out is that use a pencil. The culmination of this segment and this segment for this particular SHM gives rise to this segment. Now, since it has 2 perpendicular planes of symmetry, what we can say is like it has center of symmetry, and that center of symmetry is right this point, which I will call as O. And since it has a center of symmetry
what that essentially means is, if it has a curve here like this, it also has needs to have a curve in the like diagonally opposite section in the exact same fashion. So this is the curve. We will try to locate where this curve is, and more important than that, we will try to show that a similar movement in both of this circle will lead to this segment, and we won't be using maths for that. We will just be using some basic mirroring and stuffs to so that there is another uh, segment in these two circles which will lead to this segment. And to find that, what we need to understand is that when we take mirror of a particular thing, especially a particular 2D thing twice, or maybe any 3D thing twice, it leads to the same figure. So we can do a similar kind of stuff in this figure to find exactly that. So what we will do is, first we will take the mirror of this whole thing with respect to a mirror which is kept, this is assumed to be kept on this side, and then we will take the image of the situation with a mirror that is assumed to be kept on this side. So when we do exactly that, I will be drawing a rough sketch of how that looks right here, and for that I need to have a darker pen. Let me bring that. Essentially I bought this cute little 4 different color sketch pens, and they are cute, right? And let's move back to the topic. So, and they don't go like this. What's the matter with me? Yeah, so what I was saying is that when you take the image of this whole situation with this mirror, you get I will draw in a miniature version of what we get actually. So you get a circle, another circle, and the exact same figure but flipped. Hope you get what I'm trying. This is darker. I think that this will work. But what will we get is that since we have darkened this portion of the curve, now this portion of the curve will be darkened, and this arrow, this arrowed curve will be this one now, and the angle will still remain theta, which is like 30 degree, and for this one it will go right here in this direction, and this one goes in this direction. Now when we take the image again with this mirror, what happens is we get another circle right here, the same figure but flipped, and now this arrow comes right here. This segment is corresponds to this segment, and this segment corresponds to like this one. And what we can essentially do is like take this circle over to this side. So what I'm saying is that this side. Now what's the scenario is that for this segment we have the culmination of Okay, I will also bring this up. So it's like right here. Now we have for uh, this particular thing 30 degree, and this particular segment of 90 degrees will act to form this segment, which in this figure it's exactly that, like you can take those circle and keep those above them above them and then trace out the exact thing. So what you get is for this segment you need to have this segment of the first SHM and like this segment of the second SHM. So yeah, basically you can do that for any quarters of this SHM. And so yeah, that's basically it. For any segment in the upper half of this figure, you can always find a similar but inversed figure on the opposite side. I mean the segment on the opposite side, which is actually found due to interplay of some other sets of motion in these two figures. Like, and these are uh, like always, not almost always, but always diagonally opposite. For example, for this portion of the curve, you needed this segment and this segment, right? However, what we found out that for this segment of the motion, you needed exactly the diagonally opposite, which is this portion, this whole portion, and diagonally opposite again this portion of the figure. That's quite interesting, isn't it? uh, that was all for the figures, the lissajou figures which have um, two perpendicular planes of symmetry. Now let's move to those lissajou figures which have like only one perpendicular to the figure plane of symmetry.
So essentially what we did is we segregated the figure with respect to planes of symmetry and then evaluated each segment in the quarter individually, right, and tried to find out symmetry. Also notice the segments that we chose, like I don't have it here, but you can always rewind and check. You can notice that the segments that we chose were each a whole number of quarters of one of the phases, like here also you can check that out. Like we will take this as one of the segments, and you can simply check that out, like it is actually 1/4 of this phasor. Like in for this example is this, but in the other example, like the previous one, it was also, I guess, one of the upper circles, I mean quarter. um, Even this time around, I mean this particular case where there is a single plane of symmetry, we will stick to that approach. uh, well, this is the plane, I mean this is the plane, or if stated visually, line of symmetry. This is the segment that we will be discussing, and also notice how it describes a quarter of this phasor. Now just follow my pointers and note the specific positions in the phasor which lead to our selected segments. Check that video. will notice that these are the segments. I mean, this one, not fully till this, like some angle which I will say as like theta, and on this phasor it will be like this one, the whole 90-degree one, because that is what we chose. Yeah. Now let's do the same exercise, as in like take the mirror. I will take the mirror like and draw it below this figure. Let's do it. So yeah, this will be the lissajou figure, and this is one of the phasors, and this will be another of the phasor. I don't go on the circle, like I don't draw properly, but still you get the essence, right? If I see properly, yeah. Theta, I mean this theta, not 0, and also not q, and you will find it this one. Yeah, this is it. So this all, and now if you notice the darkened part, I mean this part has come to the left, like right here, and we are exactly able to see when the phasors lead to this situation without even going to the mathematics of it. Yeah, that's right. And oh, I forgot to about theta. So see, since this phasor moved by 90 degree, I mean the arrow of this phasor moved by 90 degree, and the ratio of the frequencies is 2:3, as is chosen in our special lissajou figure. Theta needs to be 60 degrees because it's simple ratio and proportion, right? Like it is 90 degree, then it has to be 60 degree for the ratio to be 3:2. So basically just mirror and see, and you will be able to find that it is because similar motion during different movement but only on the opposite side that lead to this unmatched satisfying symmetry in LF, which stands for lissajou figure. If you see above, you can find the exact pairs of the movement in a particular both of the phasors that lead to a particular segment, and see how even they are so symmetrically placed. Like for this particular segment, you have this movement and this movement on the upper side, and for this one you exactly have the mirror version, like this part, which is again 60 degrees, and this part. And also notice that for this whole part you actually have this 240 degrees, full 240 degrees of this phasor, and you have actually 360 degrees of this phasor. So like if you follow my hand, as I move from this point to this point, I actually pass by like 180 degrees of this rotation. Like if you see, when I go from here, I mean not from here, let's go from here to here. So when I go from here to here, I first move from here to here, here to this point, and that leads to this point, and then another this rotation which leads me back to this point. And again for this particular curve, we again retrace it, like come from this point to the uh, bottommost point, and the curve that it traces is this one. So it's like one rotation and this whole figure is formed. Now let's see how many rotations this arrow needs to perform to form this figure. Like if you again start from here, you need to go from this point, from the right extreme to the left extreme, which will be somewhere like right here. So for that you need to move from this point to this point, which is 180 degrees. And then from here to here you need to move again 180 degrees, you reach here. And then again from this point to this point you need to move like 180 degrees. So again you go there. So it's like 1.5 rotations, right? So 1 is to 1.5, which is 2 is to 3. That is what our omega is, and that's what our angle of rotation, which is theta, need to be. And don't consider this is just my phone, and this is my, I forgot to crop that out. By the way, adios. I know that my quality is not good right now, because it's some of my initial videos. I don't really know how to explain things, but I can make it certain that it will improve in the future, maybe in the near future too. I'll try to improve it like before end of January next year.